How's it going? Hello, 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 hello. Welcome. Welcome. Today's going to be a fun day. Today we're going to learn about convolutional neural networks. I kind of veered away from the syllabus a little bit just because this was right after the GBM. And I expect some people to come in here. If you did come in from the GBM, please, welcome. This is the GAITOR Club. If you want to type in chat, subscribe. I look at the Discord often, a bit of a Discord junkie. And today I actually posted a link to download a bunch of images, about a gigabyte. Not bad in terms of data. I'm about to post this in the chat, this link to the Google Drive file. Just to get started, let's get all you guys ready to start uploading this to the actual Google Drive. So if you've downloaded it, so if you go to the link that I just sent, you can click download, let that download, and then once it's done, just go and upload it to your Google Drive or open up week 3 test. Here we're going to want to go to let's see, open notebook, and then GitHub, and then in the YouTube description there's going to be a link to the GitHub repository. I'm just going to click this, just put that link in right here, and then you can open up week 3, week 3, and then go to the files, connect to a runtime, and then if you upload it to your Google Drive, click this. If you did not upload it to your Google Drive, then just take the images zip that you downloaded and then just put it into here like that. I'm not going to do that because I'm uploading to the stream right now, but I did upload it to my Google Drive. So yeah, I'm just going to mount my drive. Oh, yeah, run anyway. All right. Oh, that sucks. Hold on. Let's go back. Leave. I'm actually going to use this one today just because it was working in here earlier. All right, so let's get started. So today I'm going to start with so this is ML Monday week 3. Hello, hello. So today's going to be a little bit more theory, what an actual neural network is. If you guys have any questions, I'm going to be going kind of fast, just because neural networks is such a large topic, and it's kind of rough if you don't understand everything. However, let's get right into it. So today we're going to start by talking about what are neural networks. Let me move my camera. Then we're going to talk about what are convolutions. So if we stick those two together, we get something called a convolutional neural network, which is the main topic for today. And then once we're done talking about what a convolutional neural network is, we're going to talk about how to find and collect images. Today we should hopefully get to importing image data, which is what I just went through. If you didn't see the link, it's in the chat. Oh, hello Wes, welcome back. We love it. If you didn't see, I posted the link in the description and also in the chat to the image files that we were going to use today. If we get there, you guys don't have a bunch of questions, which I'm hoping you guys do because this is going to be the main topic. So now we're going to talk about what are neural networks. So I'm sure you guys have seen something like this before. This is basically what a neural network is. It has layers. It has an input layer. It has a hidden layer, which does all the calculations, and then there's an output layer. All of the input layers go to all of the hidden layers, and all of the hidden layers determine the output layer. Technically, these hidden layers are in themselves output layers, but yeah, you guys have seen all this before. If you haven't, then you're going to learn about it, and this is going to be great. All right, so let's go on to the next. So have you guys ever seen this before? This is what an actual neural network looks like. This is what all the variables look like. This is how it kind of works. I'm actually going to move this down here in the corner. So essentially we have these inputs, which are just variables, and we have these weights, biases. I'm going to talk about all this stuff in depth pretty soon, but what you basically need to know is that machine learning is no different than just having a function. It's not much different, and it's meant to sort of make a sort of image of what a neuron does in your body. There's inputs like when you see, when you touch, when you smell. All those are technically inputs that go into your brain, and your brain determines what to do based off of neurons that go to your arms, go to your legs. Our brain is basically just like a biological computer. And essentially what we aim to do with machine learning is to mimic how these brains work. We have an input, it goes to some type of function, which is like the nucleus cell body, that would just sort of add the weights of what's going in through the neurons, and then the outputs, the actual terminals that output what your body does. So now that we kind of understand like what the goal is, we want to mimic a neuron. Let's talk about inputs and outputs. So here I'm going to take away all the middle stuff from that one picture, and I'm going to show you guys what an input is. An input is technically just a list of numbers most of the time. Sometimes it's not, but I probably won't be doing any projects where it's not just a number. However, there is you can do things like text. You can do things like certain things, but for right now, we're just going to say that the input for a neural network is a list of numbers because it doesn't veer off that very much. And if you were to define a function f of x that outputs some output y, the inputs would be the x, right? So all you're doing here is you're just creating an input, and then the function that creates the output is just the neural network, which is pretty cool. Pretty cool that basically what we're trying to find is just we're just trying to find the right function that creates the correct output for what you give the sort of right input, which is very similar to what a brain does. If you see a bunch of, I don't know, dogs, and you want to output, say, dog from your mouth, right? You want to say dog. So essentially what we're doing is we're basically creating our own little brain that we can teach and learn things, that can learn things, right? And so images can be broken down into a list of numbers. We will talk about this later, how an image is stored in a computer, which is very important for convolutional neural networks because that will all kind of help you guys understand, what it is that computers are actually doing when they do sort of image processing. So yeah, if you look at an image, it's just every pixel has its own little number. Let me move this here. Sorry about that, guys. Yeah, so as you can see, it's just its own little number. Each like little black dot has a pointer and so on. So let's go to the next thing. What are weights and biases? So I kept these inputs in here. All these inputs have technically a weight and a bias, right? So I know it might seem a little bit weird, but the weights are actually the lines when you're drawing out a neural network. They're not the circles because there's something called biases. Now, weights scale the sort of input of a function, and these weights can be whatever. They're predetermined. They can sort of be figured out as you go along. But if you say have a function f of x times the weight w is equal to y, that's basically what you're doing to it, is you're taking a function and you're scaling this function, which we will talk about later, what this kind of looks like on a graph. And you're basically just adding all the outputs of this function together. So the circles are the biases. The biases shift the function, which we will also talk about later. And it creates this, we basically input into a function, or what you guys are going to learn, an activation function later on, what that is, and how we can kind of scale our function to fit a certain way that the sort of input data looks like, so it can create the right output. So let's talk about what activation functions are. So activation functions kind of try and fit to what the inputs look like, right? So they want to try and fit what it's kind of like, do you guys know what a linear regression is? We'll talk about that later, but essentially an activation function is the type of function that you want to fit to your input data. What's the difference between a weight and bias? The math looks very similar for both. I will talk about that later. So the main difference is one scales and one shifts. And we will talk about that later. That's actually on the next slide, Wes, when I get to you. So we have this function x. So before we define the x, oh, no worries, Wes. I appreciate you guys asking questions. I appreciate it. We already defined what x was, and we defined what y was. And the function is basically this middle part right here. What we're looking at is the function, what in a neural network is implemented, essentially, right? So we come here, and we kind of say we could do different types of activation, different types of activations, right? We can do linear activations, which is basically just a linear regression model, where you're trying to find a bunch of data and fit it to a certain line, right? But you could also have rectified linear units, or a ReLU, which we will use actually, where it basically just determines a max between 0 and some number, and it gives you a max. So if you're trying to categorize something, you would probably use this. You have tangent. This is more of a regression model, but you can kind of see, well, inverse tangent, sorry, which is actually defined right here, if you were to plug that into your equation. And you also have a sigmoid function. So basically all we're trying to do is just trying to fit these neurons, each neuron, into its own little linear regression. So it's just a bunch of regressions all in one, essentially, right? So there's many more types of activation functions. We will talk about quite a few of them in our future lectures. But for right now, we're just going to kind of stick with these because they're really, oh, let me hide my camera. We're just going to kind of stick with these because these are pretty similar in general. All right. So I just thought this was cool to see the different types of functions, like how they are affected and everything. But here's what changing the weights does. Wes, this was the answer to your question. It wasn't the next slide. My bad. Unfortunately, let me turn back on my camera. But essentially, what we're doing here is when we change the weight of a function, say we have a function sigmoid, we're changing the input that goes into that function. We're not changing the function itself, so that function does not really change. This is our sigmoid activation function where we define sigmoid as f, right? And so we have the weight w, the input x, and so on. And if we defined our sort of input as sigmoid w weight times our x inside of there, you can see it kind of scales this function up and down. Now see, if this was a linear function, it wouldn't really scale anything. It would just kind of move the functions up and down, right? Wouldn't really do much. But if you have something like, so like as you can see, the w here is at 1/2 and it scales a little bit down, and the w here is at 2 and it goes away, right? So we can kind of fit our data to be around these sort of data lines, right? And what we need to do next is figure out what happens when you change a bias, right? So we're going to use the same function sigmoid, right? And we're trying to fit these functions based off of where they are, right? And what we want to do is we essentially want to move these functions based off of where they go. So same deal, we just add a bias, where the sigmoid is wx times b, which at this point we move them left and right. So the difference essentially is basically all we want to do is either scale the function up or scale the function down, which in turn also changes the function. So I don't know if you guys had this in algebra or whatever, but if you were to like multiply something by the x, you would have to show that on a graph. Well, it's just the same way. It changes the way the function outputs based off of, whatever, based off of the x. It moves what the function looks like, and it tries to fit it to the data. So now we can kind of see the whole picture, right? Where we have this hidden layer, and then all these hidden layers are connected to, we have this input layer, and all these input layers are connected to every single one of the hidden layers, and all these have weights, right? And then this bias, what is also randomly calculated, kind of shifts the graph the way we want it to, essentially, right? So now that we kind of have a larger picture of what's happening, and why it's actually creating an output, what's actually happening. Okay. So basically what we can do is say, now that we kind of understand what neural networks are, if you guys have any questions, please let me know. I love talking about this stuff. And to answer in chat, you basically have to subscribe. That's all you got to do, and then you can ask me a question in chat while I'm live streaming. But to talk about convolutions, we have to talk about how image data is actually stored, right? So I showed this picture before. Essentially, in an image, it's just a bunch of numbers, right? Same as when your eye senses something, it just inputs a bunch of data, and it wants to create some sort of and it basically has a number for each individual part, and essentially, like this dog image here, right, is just made up of red, green, and blue channels, right? So there's 3 different channels, 3 different numbers. Are the hidden layers user set or computer generated? So that's the thing. These hidden layers are randomly generated, and then when you have this, when you have like randomly generated layers, right, you have this like base point, right? And then what the computer does is it uses that base point to kind of find, which layers like helped the most, and then it changes the ones that help the least, right? It keeps the ones that help the most and changes the ones that help the least. And that's called a loss function to determine the loss. We will talk about that in the next lecture. This lecture, I think I had time for that, but there is something called a loss function, and it helps us understand whether or not we're doing good, we're actually improving. So back to how a sort of image is stored. You have 3 different channels, right? You have the red, green, and blue channel. You could just have a white and black channel. It depends on the image, but most of the time, especially today, nowadays, your images are stored in 3 main channels, right? And then these 3 channels kind of stack on top of each other, and you can see what each channel will kind of look like. So this is an example with a dog, right? And then so all these channels come together to create that one image. All right. Finally, what are convolutions? So this is a really good GIF that I thought kind of helped me understand what it was, what a convolution actually was. And essentially, it's just having like a function and computing that function into a smaller portion of that function, so it's easier for the computer to deal with, right? So if that's like changing an image from black to white, that's technically a convolution. If it's adding more white to it, if it's adding more hue, more saturation, those are all convolutions. They change the way the image looks in a uniform manner. That's basically what a convolution is. And just so we can kind of see the math, how it's kind of doing this. So if you guys took like linear algebra or anything, basically we have an image, which is a big matrix, and then we have a convolutional matrix, which kind of changes the actual the way the image looks, and we basically just go like from one sort of index to the next index, and we generate a new image. So if our filter was 3, 3, and our image is 6, 6, and we plug this matrix in here, the sum of the convolution will be -7. is this generated white block our f? Yes. So so it's very similar to how a neural network works. The convolution itself is just a function, right? It takes in an input and outputs something different, right? And every input has its own sort of output, right? And which is really cool. It's very similar to a neural network, which is why we use them almost interchangeably. Not really, but kind of. And so yeah, our white block here is not our f. So this white block here would be our y, and then this function, the convolution that we're throwing on it, the filter, would be the f, right? We would be changing it based off of what this filter says. All right. So basically what this does is it does something like it extracts features in an image, so it's easier for the computer to understand how these images kind of what's important in these images, right? Which is what we need to send it into a neural network. And that's all fine and dandy. We we have like all these sort of features. Now, what do we do with these features? We do something called feature learning, right? So we allow these convolutions to change, be randomly generated, and generate themselves through the actual sort of input. So the difference here is that this feature learning, so before our convolutions were defined by us, if we wanted like all the vertical differences versus all the horizontal differences, but in something like feature learning, the neural network itself actually determines what convolutions you are using, which is really, really useful. And basically, let me see, what does this do? So basically a convolution, it's just a layer that changes the sort of way that an output looks. So sort of changes the way an input looks, right? So it's basically not much different than a neural network. It's just a neural network doesn't have it's not a matrix. It only has a weight and a bias. It's essentially the difference. And so if you look here, like machine learning is more of doing the actual feature extraction yourself, figuring out what features to put into the actual neural network itself. But deep learning is letting the neural network figure out what features that it likes. It's doing it for you. There's a big difference. And this basically allows you to just give your computer a bunch of input and it just learns. It just kind of learns. This deep learning stuff, we use Tensorflow, which we're going to learn maybe in this lecture if we have time, but the next lecture for sure. Sorry about that burp. Whoops. EXP error. So now that we've kind of talked about what a convolutional neural network is, if you guys have any questions, I'm going to kind of pull up the actual, hold on, let's see. I'm going to pull up the file that I need. Okay. Please, if you guys have any questions, let me know. I really love this stuff. And we're going to start talking about, also, while we're here, please subscribe. That would be very helpful. I'm trying to get, I am only going to do these unless people actually watch them. For training, is there a larger requirement for initial data points to train machine learning compared to the initial data requirements for deep learning? So there's no requirement. Like, it's kind of like whatever works, you know, like if you're training and you're only getting like 60 to 70% accuracy, based off of your inputs, then that's probably you need more data. But it could also mean that if you're on like your 200th sort of learning cycle and you're not improving at all, it could be the neural network is the issue. There's a lot of could be's inside of machine learning, which is kind of what is. It's kind of a gray area. I wish I could tell you a more straight answer, but I really can't. It's all up to interpretation. I actually want to go back and talk to you guys a little bit more about, hold on, what these activation functions are, right? Because these are pretty important. All right, so I'm going to pull up here the activation functions, and then I'm going to show you guys where you can find the actual activation functions yourself. So here, I'm pulling up the week 3 notebook. You can see right here all this stuff that we're going to do today. So let's go here, down here. All right, so essentially, let's see what we got here. All right, so we have all these activation functions, right? Let me go back. Let's see. Optimizers? No. We have metrics. Give me a second. I'm trying to find what the actual thing is. Hold on. I'm trying to find it. Sorry, I didn't think I'd actually talk about this, but okay, here it is. So here's a list of the TensorFlow activations. Screen, go like this. Right, so here's a list of the TensorFlow activations that we can do. You see we have an exponential linear unit, we have an exponential activation function, which I guess, yeah, deserialize, which is basically if you're dealing with strings. You have a Gaussian error linear unit, which is just basically a normal graph. Get just returns a function. You can make whatever function you want. Hard sigmoid is the sigmoid function. Linear is the linear function. Rectified linear unit sort of establishes a max and then becomes a linear unit, linear function. Scaled linear unit, which is basically like if you had a linear unit but you also scaled it, which I don't use very often. Sigmoid, softmax, all this stuff, right? So this is all stuff that is pre-made by TensorFlow. We don't have to do ourselves, which is amazing. Most of the stuff that you will use is already pre-made, which is amazing. And we thank the smart guys that made it. So now let's go back to the presentation. Let's go, wait, hold on. Bada bing, bada boom. Why did it not show up? Oh, here it is. Okay, so now that we're back to the presentation, let's talk about what we're gonna do to find some data, right? So how do we find data? So find and collect images. So I got my image data set this time around from something called Kaggle. Kaggle is it's actually a Google company. Google bought it out. And essentially it allows you to go in here and see, you know, all this type of data. So I got it from this data set. You don't need to go to this data set, but it is a good example. Let me see. Let me see if there's an example. Yeah, so just some pictures of dogs and how to do it. And one of the great things about Kaggle is you can actually go in and see the notebook used to, and like what the outputs of the notebook were and how all this stuff works. It's a great resource, and I think everybody in the club should either create an account or use it. I use it all the time just to see projects that people are working on, just see the type of data that we can see. So now that we've talked about Keras or Kaggle, there's another thing that we can use, and that is, let's go back. Where is it? Oh, here it is. There is also the Google search engine. And literally any search engine, you can go here, and if you want to say find dogs, put in dog, go to images, and you can go see all these dogs, you know? So let's go here. Let's actually go right there. Right, so we can see all these dogs, right? But there's this plugin called Image Downloader, right? I linked it in the description. If you guys go to the Google Apps, the Google Extension Store, you can go here and you can kind of see. You can look up Image Downloader. I also linked it in the description, but just so you guys can see it, this is the app. It has over 1 million users. It's a great extension. But you basically, once you've added it, which should be a button right here, you go over here and you can see all the images on this page. So say you want this dog, that dog, that dog, that dog, that dog, all these dogs, all these images of dogs. So we don't want this one. We want this one, this one, this one, this one, this one, this one. And we can go over here and we can say download. Got it. This basically saves all the downloads into your download folder. You could go in and change the subfolder. You can add like subfolders. So like if you wanted to add like dog, and then you want to rename files, I don't know, dog, then you could also like go in here and then it'll save to a subfolder, right? So now you got dog 1, dog 2, dog 3, etc. That's a really cool resource. But I've also put inside of the GitHub a file called, let me see, I've also put in the GitHub, so I'm just going to go to week 3, folder, download images.ipynotebook. So this won't work on, this will not work on Google Colab. However, you need to install something called Selenium. Selenium you need to install. There's install instructions here. You basically need to install the browser. Basically need to install the browser, drivers, well, the library. Then you need to install the drivers. And then once you have those drivers, you can do whatever you want. You basically need to pay attention though to where the actual driver was downloaded, because you will need that right here. And so you basically want to go find where your driver is. In this case, I put it in my users development, and then I put it right here. A little trick: if you're on Windows and or on Mac, you can go to the properties and you can actually get the location and actual name of it. But also you can say copy as path, and then you can just copy and then paste this in. Okay, so now that we have that, and we have the driver set up and everything, which I really don't expect you guys to follow along with me, just because I already have everything all set up, is essentially, I mean, if you want to follow along with this one, you can. It's a great way to learn. Just follow along, do it yourself, DIY. We basically do the same thing. We just say dog, and it will start downloading dogs into this file folder. So it opens up Firefox, and it just starts scrolling through Google Images, and it does all that for me. I'm not touching it. It'll download all the images. And then it'll save all those images to files automatically. So I already created this. I'm not going to do this anymore. There's no reason for me to do that. But because we have this Kaggle dataset, which has much more than if you guys were to do that. I've run something like that overnight, and it hasn't gone anywhere near the amount of data that the Kaggle person found. I don't even know where he got it, but if you look into the Kaggle data that I uploaded to Google Drive into an images zip, it might not be called images, but it will come out in an images folder. And we go through and we look at the sort of directory structure of this folder. So I'm going to change this to be more of a details tiles. No, I don't want tiles. I want content. No. I wish they don't have it in this, do they? Oh, well, okay, so we're just going to look inside train. Inside of train, we have 2 folders, cat and dog. These are the classifications that we want. And I'll show you guys how to import them by their own classifications later. But basically, this is just a bunch of pictures of dogs. About a gigabyte of dogs and cats. And you can see how many we have by just going to, like, say, dog and looking at properties. And there's 12,000 files. I don't know if you guys can see that, but dang, that's a lot of files, isn't it? 12,500 pictures of dogs. What are you going to do with that? Well, the answer is make a neural network. That's the answer, which is the goal of the entire thing. So basically, what we want to do is take these images, right? And then we can go here, and then I'm just going to show one of the images from the train. So we saw this image already. We go here and we can see, boom. If you're on Windows, if you're on Mac, the directory structure is a little bit different. We have this. If you're on Windows, the directory structure is backslashes, which that's just Windows. That's how they are. But you don't need that. You could also use a library in Python called OS, which comes with every Python installation. It's part of the standard. And you could just say what your current directory is, which is dot. Dot meaning, dot basically means your current directory. And then double dot means the parent directory, which goes to the directory above it. So if I were to be in here, dog would be the directory I'm talking about, and then the parent directory would be train, what it's inside. So if you guys don't know what directory structures are, that's basically the idea behind it. And yeah, so that's basically all you got to do to download some images of dogs and cats. So now that we have some images of dogs and cats, oh wait, what do we see? We see, what's up, Wes? Of course Google bought it out. What else would you expect? Yeah, of course, they buy all the data. Because Google looks at data like this. Data everywhere. And then they just buy it all, you know? It doesn't matter what company it is. Doesn't matter what company it is. If they have a bunch of data that they don't have, they will buy it. That's how Google works. But essentially, I wrote this inside of the actual... so I'm going to do this one actually inside of... I have a lot of windows inside of the actual, let me go here. Oh, here it is. Okay, so I'm going to go inside here. And what I'm going to do is I'm going to unzip this file, right? So my drive is on here. And inside of my drive, I've uploaded the, what is it? The zip file that we need, this images.zip, right? And so once we have that, if you want, you can just upload the images.zip. I talked about this earlier. You just go download wherever you downloaded the images.zip from the Google Drive link that I sent in chat earlier. I'll resend it. You can go there, upload it, find some date, wait for it to upload. I'm sorry, I can't help you guys make it any faster. The fastest thing I can think of is making this here. But essentially what this does is it mounts the Google Drive onto your thing, and then it is able to, again, unzip the images file inside of your thing, which is exactly what I have for my data here. So we'll just wait for that to run. It should propagate here pretty quick. Let me see. As you can see, you can kind of see your data structure here, of what your files look like. So I have all this code in the week 3 actual files. So yeah, here it is. Where is it? I lost it again. All right, here it is. So you can see you got all these different cats and everything. You see cat0.jpg, cat1.jpg. That's a weird picture. Whoops. All right. So we have all these images. We can view these. Make sure we can actually view these here. Oh, there they are. So what does this code do? Essentially, what this code does is it takes your current it takes whatever file, so wherever your images.zip is, this can be wherever, and it extracts it to where your notebook currently is located. That's basically what it does, which would make it so all the rest of these actual cells will work. As you can see, yeah, here it is. The dog, the little dog. Look at how cute he is. Little chocolate lab. Look at him. Adorable. But now let's talk about TensorFlow. So what we're going to do for the first time is we're going to import TensorFlow. We just import. I normally import TensorFlow as TF. And then I say where my data is, right? I define, this basically just adds directories. So this is in the current directory, images, and train. You do whatever folder you want, but the idea is that these are in their own directories, so you sort of sort them out in your folders based off of what categories you want them to be, and then TensorFlow, Keras will do the rest for you. It will categorize them based off of their folders and do all that. So if we just run this, this will open up something called a dataset. Let me just type dataset. Right, so if we have a dataset type, batch dataset, this basically, it doesn't actually load the files into your system, which it's kind of weird. It creates something called a generator, which we talked about in the introduction. It's just a function that tries to actually view. It doesn't actually load all the files into RAM. It just gets a list of all the files and gets them ready to load into RAM. And if you go to week 3, we do this thing where we have a validation split, which we talked about in the last lecture, if you guys were not there, where we basically split the training and validation subsets. You can learn a lot more about this in the documentation. There's a lot of stuff here. There's a lot of good examples. But essentially, after we've run this, we can go here and we can print out some of the stuff from our data set. Here, let's go back. So we can import some of this stuff from our data set, and we can, again, copy and paste in here. We get our class names and cat and dog, and then we get some images randomly generated just from our data set. So that's pretty cool. That's basically how you import images from a file system inside of TensorFlow, which is pretty easy. You basically just need to define what directory you want them to go in. You need to make sure that your directory has different classifications, and then you just need to say what subset it is. So if I were to create a valid and trained data set, right? Here, we would have to make 2 different variables. One's a generator for the validation, and one is a generator for the training, which is wild. We could just create 2 generators that easily from our data, but it's true. And essentially, you can go here. You can do stuff like change what label it is. You can change the batch size, the image size, whether or not you want to shuffle the data. We don't shuffle the data because we have two data sets. But if you had, say, a data set that was like in its own sort of folder, like train, and then so you had like a train dating set and a validation data set, which we do have, but this was the data I got from the Google search. We could use this as validation, but we're just going to split it and use it as that. So yeah, but once we've done that, we can go here and we can create this train and valid data sets. As you can see, the train data set has 18,750 files, and the validation data set has 6,250 files, which is just, again, this is 75%, this is 25%. Pretty easy to figure out. And then we have the interpolation mode, which is just how it scales the images, because it has to go, they all have to be to the same size, which is important, because when we go to actually plug in the data set, which I will go here, when we go to actually plug in the data set, let me move this back. We go to actually plug in the data set, we'll get something like this, where we can have an input, but these inputs have to be the same every time, right? It has to be the same length every time for an input, right? Which is kind of annoying, but makes sense. You know, considering like if you created a function, you just didn't have all the inputs that you needed, it wouldn't be the same function, you know, if it didn't have all the inputs. But we will learn about something that can take different amounts of inputs, and that's something called a transformer, and that's mainly used for natural language processing and other types of data. So let's go back. I really don't want to start on the actual training yet, but I can talk about what we are going to do, because the training, I haven't figured out how to get it so it gets to like a solid like 90% accuracy yet, and we'll talk about that next week. But here's how the image classification layers are going to be set up. So we basically have three convolution layers, which we call feature extractors. Each of these has a convolution, which is just a randomly generated matrix, and then it does this thing called a batch normalization, where it basically just takes the output of the convolution and scales it between 0 and 1, because it's not guaranteed that it could scale them differently, but it's really up to interpretation how the weights and biases turn out for each convolution, right? Well, not weights and biases, how like the matrix is scaling everything. But what a normalization does is it basically normalizes it between 0 and 1. And then there's a pooling layer where it kind of just so all this batch normalization and convolution and everything, that all happens in a layer. Yes, we do like normal distributions, indeed, Wes, indeed. So let me go back to my screen, actually. So yes, we do like normal distributions. And so basically what happens is we have this pooling where it, instead of having each individual pixel, when we pool it, it turns it into that 2D array again. And then dropout makes it so it actually takes out a certain percentage of the actual what should we call it? So it takes out 25% it randomly takes out 25% of the convolutions every single time. So we aren't reliant on a certain convolution. So that way it like generates, it tries to fix all of the different convolutions instead of just relying on one main convolution, the weights being all weird. But let's go back to here. We have this, so we have three layers of this. The first layer we go, it creates a 32 by 32 image basically, and it uses the activation ReLU, which we talked about earlier. rectified linear unit. It has a max, and it creates a linear component to create some sort of way for the convolution to change what the image looks like for the neural network. And we have 3 of these. Basically, what we want to do is think what's the computer going to do, right? So for this first one, we kind of want it to say take out colors, or like change what like the face looks like the actual facial features, right? This next one would be something like you know, what its body looks like, or how like more facial features or something like that. But essentially what we want to do is we want to find what each we want to essentially create these convolutions so that they are easily scalable, and then at the very end, right before we put it into this dense, which we will talk about later, dense, which is the type of function that we will use for finding out, which is like the actual neural network weights and biases part of the lecture. We will essentially take all these, flatten them. What flatten basically does is it takes it from a 2D vector where the convolution needs to know, like, you know, what sort of parts of the sort of image are. So for a convolution, it needs to be 2D. For a neural network, it needs to be 1D. And what flattening does is it just puts all those into a flattened neural network. Dense is the actual neural network itself. And again, we drop out some of those dense neurons with so like 25%. Basically, like we drop some neurons so we aren't really reliant on some of them, and then we do another dense right after the dropout. So let's take a look at that again. So basically, we create this model, right? And then after we create a model, let's just go up here. So once we create this model, I might actually go on not live if I accidentally run this too fast, but basically what we're gonna do now, we have a summary. We have the convolutions. It tells us our output shape, the number of parameters that each one has. It tells us, you know, how, like, so like the batch normalization, all it does is it just, again, scales it from between 0 and 1, and it is the same shape as the convolution. So, but it has less parameters because the parameters in here are based off of the inputs, which we made our image height 128 by 128. We can go in here and change what we want, but 128 by 128 was pretty good. It looked like we could tell the difference. Like, that's a cat, that's a dog. As long as we can tell the difference, it's good enough for the model. Yeah. So let's go down to here. We have the same max pooling. Pooling just again, it just takes everything and then it changes its size or finds the max. It depends on what kind of pooling you're doing. We're doing max pooling, so it just finds, like, if there were like 4 pixels, it just finds the max pixel and uses that one. And so for dropout, what is that conv 2D growing in size? Sorry if that sounds dumb. It doesn't sound dumb. So the reason you would want like a convolutional neural network to increase in size would be something like if, say, like your images are a little bit so like we only had 128 by 128 sort of images. So the convolutional neural network, this isn't the convolutional neural, so 32 by 32 is like the size that we get from, let me go back here, the size that we get from, where is the convolution? Here. So the 32 by 32 isn't the output size, it's the input size. So the convolution here, so the convolution 2D would be like 32 by 32, right? And then that would be a randomly generated convolution. Okay? And then, does that make sense? So we're basically going from local features to like semi-local features. So we're going from like local features to like semi-local features to like the entire image, right? So essentially what we're doing is we're creating like kind of like how your eyes work, you know? You have like a focus point, right? And then your eyes also kind of see out, and then they kind of see the whole image, but you really have like a focus point. The first convolutional layer would be like your focus point, right? Like where is the computer actually focusing? And that's the entire thing, right? So it's focusing on a certain part of an image, and it's generating an output. Does that make sense? Okay, so hopefully that made sense if you're still here. All right, so let's go here. Let's go back. Now that we have this summary, and it says total params, so you can see this dense parameter is really high because it's right after the flatten, and then we have this flatten, and then this would be, so a dense layer. So let me pull out a calculator. So if we have like this dense layer here, right? Boom, 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 boom. And then we have the number that's after the flatten, and then we multiply that by 512. We get that 12,845,056. Whoa. There might be a difference in that, but I don't know why that's not the same. I don't know. Essentially, basically, it's close enough. But essentially, what we're doing is we're making it like we're taking every single input here, and we're giving every single input a weight to our hidden layer, which is our dense layer, right? And then we're taking this batch normalization, which just does the same thing. It takes the max, creates a sort of image. This only has 4,020 parameters, and that's just taking like the 4 max from like the sort of max images, the max parts of the image. And then we're doing the same thing, drop out, making half of them, or sorry, 25% of them not work, whatever you set this number to. And then we're going to output categories, either 1, 2, which in this case we had 2 categories because it's dog or cat classes. And then we take this thing called a softmax, which just whichever one. So like the actual output for this would be like cat probability is like 0.1, and then dog probability would be like 0.99999, right? And then it would choose the dog probability because that's the max probability that it is. It doesn't actually do like the whole whatchamacallit. It doesn't come out with just 0 or 1. It comes out with probabilities for each category. And we will learn a lot more about this next time. I just didn't have time to visualize what our actual convolution looks like this time around. But I will. In the next lecture, I'm going to take what it looks like after each convolution and show you guys what they do to the images. And that's pretty much it for today. We kind of learned how to create a model. We'll go much more in depth about this next time. But hopefully you guys understand what a neural network is and how it works and what a convolution is and how it works. I hope you guys liked it. For all you guys that came in live, Wes, thank you for going in the chat. I appreciate you. I wish more people showed up to this. I spent a lot of time on this. And yes, of course, Jordan, thank you for coming. You were here last time. It's good to see you again. Thank you for coming. Appreciate it. I hope you have a great afternoon. And I hope you learned something today. Yes, indeed, indeed. Oh, Joshua, thank you for coming. I appreciate it. Ria, thank you. Thank you guys for coming. I'm glad people are coming to watch these, because these take a lot of work. And I hope you guys like it. If you guys do like it, can you guys, if you can, please subscribe or like the video, if not both, you know, if you liked it. Oh, thank you, Wes. I love you too, man. Thanks for coming. You're the best. And yeah, that's basically, that's it today. It's 7:30. If you guys have any questions, please let me know. If not, I hope you have a wonderful afternoon. And yeah, this is to be continued. Oh, of course, Ria. Thank you. I appreciate it. Yeah, no, I basically make this so people watch it. I've learned a lot of this doing research, and I just want to help people understand how it all works, you know. I hope you guys understood what I was saying. I went a little fast, I think, but you know, sometimes if people go fast, it helps me understand more, just because, you know, they're going fast, you know, getting all the information. They aren't going around the bush, you know. Oh, thank you, Wes. I appreciate it. Let's see if my program fundamentals teacher can send out a link to this video. Thank you. I appreciate it. Yeah, if you guys share the video, it helps a lot. Liking the video helps a lot, especially with the YouTube algorithm. God, I sound like a YouTuber, don't I? And yes, Ria, I'm glad you're watching it with two people, two other people. I hope they liked it. I hope they go back home and they like and subscribe it again right here. And yeah, hope you all have a blessed day. I think that's about it. It's 7:30 already. Wow, that went fast, didn't it? I'm gonna send out the presentation, actual link, right now. I'm gonna send this in the Discord. You guys, if you guys want it, I will put this on the actual video itself as well. Love you, Wes. I'll talk to you guys later. All right, guys, have a good one. This is to be continued. Goodbye. Love you guys.